Hey guys, this video is about the mole and introducing the conversion factors that go along with the mole. And we're going to be looking at something over the next couple of videos called the mole map and doing conversions regarding molar quantities. And this is basically a step using dimensional analysis. All right, so let's get started here. Now, what is a mole? For some kids, it's kind of complex, but essentially it's very simple. So I have a few examples we're going to look at. So a mole is the amount of a substance that contains as many particles as there are in exactly 12 grams of carbon-12. Okay, so when this all started, they decided to use carbon-12 isotope as the baseline to calculating moles, okay? All right, so now, it is impossible to count or visualize all these atoms, but we need a way to measure or observe them. Atoms are very tiny and inefficient, therefore we use mass. So you can't count them. They're too small, so we have to use a scoop of them to figure out problems with them. Okay, so let's take an example here. Very simple. Let's do like a little analogy. Okay, for example, let's picture a large room full of golf balls. Is it simple to count them? No, it's not. Therefore, we need to come up with a better way to determine how many are present. This is like atoms of an element or a compound. Okay, step one. We can fill one 5-gallon bucket with golf balls, weigh the bucket, then count how many balls are in the one bucket. So therefore we get the mass for the one bucket of golf balls. Step two, then we can multiply the number of buckets it takes to empty the room and then multiply the number of golf balls in one 5-gallon bucket from step one. Okay, so you have a room, you take the buckets and you scoop up the balls until there are no balls left, and you determine how many 5-gallon buckets you had. Then you multiply the number of 5-gallon buckets by the mass of the first weighed bucket. Okay, then you round to the correct number of significant figures. That's a way to actually simply, by mass, determine the number of golf balls. Now, are you going to have the exact number? Probably not, but you're going to be pretty close. Okay. So it's like a little analogy, like microscopic little golf balls. Okay, now um, the mole is actually based on the Italian scientist Amito Avogadro. It was based on his findings on the carbon-12 atom. He used carbon-12 since it had 6 protons and 6 electrons, and it had a mass of 12.01 grams, or 12 even units. Now, each carbon-12 atom had a mass of 1.992646547 times 10 to the negative 23 grams. That's a very, very small number. Super tiny. So how many atoms did it take to make 12.01 grams? Well, Amito Avogadro came up with this number. It took 6.02 times 10 to the 23rd atoms to equal 12 grams of carbon. So it took a massive amount of carbon atoms to make 12 grams. Each one is so tiny. And that's basically the measurement that he came up with. So 1 mole of carbon contains 6.02 times 10 to the 23rd atoms. So this is a very important number. This is like 12 eggs to 1 dozen. So this is like a dozen. Okay, so this is the number that we're going to be using, and that's where it comes from. Okay, a little more in depth than you need to know, but it's very important where this number comes from. It comes from this number. Okay, so therefore 1 mole of carbon contains 6.02 times 10 to the 23rd atoms. Or we're going to say Avogadro's number equals 6.02 times 10 to the 23rd, which is going to be a conversion factor. Okay, so now we're going to look at representative particles, which is I call the leg of the mole map. Okay, it's going to be a certain kind of calculation. Okay, what a representative particle is the smallest unit of a substance that can be broken down without altering the composition. There's 3 types, depending upon the type of matter you're looking at. Okay, the first type is atoms, which are elements like, say, gold, potassium, and neon. Any element is going to have the name atoms. Formula units is another type of representative particles. It's basically an ionic compound, like your metal and non-metal sodium chloride. So it's your cations plus anions. That's a formula unit. Now the third type is molecules or molecular compounds, which are your non-metal, non-metal. Okay, so you have your three types of representative particles: atoms, formula units, and molecules. So these are the basic names that go along with what kind of compound you're using, like gold, atoms, sodium NaCl are formula units, water are molecules, water molecules, sodium chloride formula units. Okay. Okay, so real quick, look at these right here and determine which of the three types of representative particles they all can be. So pause the video, write down atoms, formula units, or molecules for each one of these, and we'll check your answers. Okay, so you should have, check your answers. Okay, type these out for you so you can compare. Okay, now a conversion factor using the representative particle, the mole. So 1 mole of any substance contains the same amount of representative particles. Okay, any substance is going to have this specific conversion factor. Now 1 mole of X, any substance, equals 6.02 times 10 to the 23rd particles, X. Okay, so X is just basically the substance's formula, whatever it's going to be, an element, an ionic compound, or molecular formula or molecular compound is going to go where the X is located. So it's a universal formula that has to be modified every time you use it. So for example, 1 mole of silver equals 6.02 times 10 to the 23rd atoms. 1 mole of NaCl equals 6.02 times 10 to the 23rd formula units. 1 mole of water equals 6.02 times 10 to the 23rd molecules. Okay. So here's a picture of the mole map. Now the mole map essentially has 3 legs. Okay, 1, 2, 3. So we're going to look at the representative particle side. Okay, our goal is to actually be able to utilize mole in order to do one of the major steps, which is called stoichiometry. We have to be able to get whatever number we're given, whatever kind of unit it is, and be able to place it into moles. Therefore, we can use it later on. Okay. Now, this is supposed to be a simple step. It's not supposed to be anything complicated. Okay, but the mole map, and we're going to explore all these 3 avenues. Now, why it's called the mole map, you can see there's little streets, yellow dashed lines, dashed yellow lines, dashed yellow lines. And you can see there's arrows going in different directions. Well, depending upon which direction you're going, should indicate to you which conversion factor to use. So if you're going from representative particles to the mole, you're going to be using this conversion factor. If you're going from the mole to this representative particle, you're going to be using this conversion factor. Okay, so it's simple as that.